Okay, right. So just quick recap. I won't go through all of this again, but just magnetic field lines point from north to south poles. They form closed loops, and they can be produced by permanent magnets, current carrying wires, and moving charged particles. We've got the right-hand rule to tell us our thumb goes in the direction of current and our fingers curl in the direction of the magnetic field produced by that current. The left-hand rule links forces felt by moving charges, which is what current is. This turn off general. Yeah, go away. Right, so it links the forces felt by moving charges when they are in a magnetic field. So all we need to do for the left-hand rule is just remember what each one of these quantities mapped onto, well, which quantity mapped onto which finger, basically. And I think the way people usually say is that force is on your thumb, right? They sort of have the same sounding first letter. The magnetic field, how do people remember this from? I can't remember that one, but I remember that we said that current is on your second finger. So if you can remember these things to link those together, then the magnetic field just goes along your first finger. Ah, that's what it is. It's field goes like first finger. So that's just the way that you can try and remember these things. Right. Last lesson on Friday, we talked about if I have a charge Q moving at velocity V and it's going into a magnetic field, which let's say is going into this page like this, then what's going to happen is that the charged particle moves freely until it enters the region of the magnetic field. So it moves in a straight line. And then when it enters the field, it now feels a force. And if you use the left-hand rule, you'll see that that force is going to, let's check. So our first finger goes into the page, second finger points to the right, our thumb points upwards. So this is the force felt by that particle. And it has this velocity. So it's got a force perpendicular to its velocity. So it's going to move in a circle or along a circular path. And then if it reaches a region where it's no longer in the magnetic field, afterwards it's just going to carry on going in a straight line because it's now a free particle again. No force is acting on it. And we said that the force felt by that particle is equal to BQV. And then we set that equal to the centripetal force of the particle, mv squared over r. This comes up a lot in exams, right? You'll be asked about like electrons. So you're assuming that you know the charge and the mass. Or you might be asked about like a positron or a helium nucleus or something like that. Okay, right, so just a quick recap from last lesson, and now I'll get on to flux. But actually, before I do, can you all give me a thumbs up or thumbs down? Are we happy with these things? Does anyone want me to explain anything in any more detail? Awesome. Right, so because this topic is quite long and quite difficult, what we'll probably do is at the end, I'll do maybe like 2 lessons of just me going through a bunch of past paper questions, just so you can see how all this stuff links together. But for now, we'll just focus on like the content. So, magnetic flux. To understand magnetic flux, we're first of all going to imagine right, let's imagine that it is raining outside. I'm going to draw the rain like this, just coming straight down from the clouds onto the floor. All right, so hopefully you've all seen this before. I mean, we all live in the UK, so we definitely have. Right, so the rain are these little blue droplets, and I'm going to represent the fact that it is raining with these black arrows. So if it was raining even more, if it was really heavy rain, I would draw more of these arrows, right? There would be a higher density of these lines. So think about what that might mean for a magnetic field, because that is going to be the analogy here. And now what I'm going to do is I'm going to imagine, right, this is like a silly experiment that you would never actually do, but hopefully it's just going to give you all an idea of what flux is. So imagine that you've got some sort of like hula hoop. I think that's what they're called. All right, that I'm going to try and like spin around my waist like this. All right, so like you all know what this is, right? Like the plastic tube that you spin around your waist. Okay, right, and this hula hoop encloses some area like this. And now I'm basically just going to ask the question, how much water falls through this hula hoop? And that the answer to that question is essentially what magnetic flux is going to be when I put this analogy to map it onto the idea of magnetic fields. So the rain is going to be our equivalent of a magnetic field. So that's why I've drawn these black lines. These are our magnetic field lines. In this example, they're just going down our page. And then I said, if it's raining more heavily, we would add more of these field lines onto our diagram. And we know that if we've got a high density of field lines, that means that we've got a stronger field. So if it's raining more in this analogy, we've got a stronger magnetic field. So if we wanted to increase the amount of water droplets of rain that fall through this hoop, there's three things that we could do. Can anyone think of what these three things might be? Well, maybe not there's three things that we could do, but there's three things that could happen. Sam?
You could increase the density of the rain that's falling.
Good, right? So more rain. If there's more rain, then there will be more rain falling through my hula hoop. Perfect. Good. So can anyone think of anything else? Let me give you an example. Let's imagine that I have a friend next to me and they're able to do tricks with their hula hoop and sort of spin it around at an angle like this. So who gets more rain through their hoop? Me or my friend? Okay. Sorry, I haven't seen that people have been putting their hands up. Henry.
So for the other question, would it be, could you just increase the area of the just hula hoop?
Good, right? So I could buy a bigger hula hoop. If I had one that looked like this, it would capture more of that rain, or more rain would fall through it. Perfect. Thanks, Henry. Ash?
Could you also change the angle?
Perfect, right? So what angle do I want? Do I get more or does my friend get more in this situation?
You get more.
Good. Right, so we want to make sure that this angle between the plane of my hula hoop and the rain is well, we'll see what the angle is, but let's just say that we need to be careful about what this angle is here. All right, now this is essentially the idea of magnetic flux. So we're going to have some magnetic field, B, and we're going to be interested in some wire which encloses some area. And we're going to ask basically we're asking how much of that magnetic field goes through this area. And the answer to that question is this idea of flux, which gets given this symbol phi. All right, this is just a Greek letter called phi. Yeah, Sam.
Okay, so could you just repeat that one more time?
Sure. So the flux is the amount of the magnetic field which goes through the area enclosed by that wire. So in the same way that So the analogy would be the flux is the amount of rain which passes through my hula hoop. So the way to increase the flux is exactly the same. We could make our magnetic field stronger, then more of these field lines go through my area. Alternatively, right, if you imagine that this field extends all the way out here, at the minute, a lot of these field lines aren't going through my area because they're outside of the area like this. So if I increase the area enclosed by my wire, now more field lines cut through it. And then the other one is also just to make sure that the relative angle is correct. So let me just show you what I mean by this angle. If you imagine that my wire encloses an area in this direction, let's see if I've got anything useful that I can use. Right, so imagine that my phone here is the area that I'm interested in, and there's a magnetic field coming in this direction. Currently, no field lines cut through my screen. That's what I'm interested in. I want field lines to cut through my screen. That is what flux is. So the way that I get the most is by making it in this sort of perpendicular direction, where I'm perpendicular this way and I'm perpendicular this way too. If there's any sort of relative angle like this, then I get less and less flux. You can see that if I'm at this angle, I don't cut through it at all. I don't go through the screen. I go like I glance along the screen. All right, let's pause here, and anyone who's got any questions can go ahead and ask. No? Okay, cool. So now let's think about this angle here. So what I'm going to do is remove these stick people. I'm going to draw these two hula hoops. Like this, right? So you're going to have to imagine that they are the same area. Let me just redraw it so I don't confuse anybody. So I'm going to draw a vector out of these surfaces that is perpendicular to the surface at every point. So the way that I usually represent this is imagine that my face is that surface. My nose points in the direction of that red vector that I've just drawn. Right, so that vector tells me in what direction is my face pointing. That's one way to think about it. And any line which you draw on that surface is perpendicular to this vector. So any line which I draw, they're all perpendicular to this vector. Right, we don't need to worry too much about this vector. All it's used for is to define this angle that I said we're going to be interested in. That angle is going to be the angle between the magnetic field and that vector, which I'm going to call theta. So my magnetic field goes along the same direction as that vector in this case. So here, theta equals 0. Or you can think of it as being 180 as well. So with all of these different variables defined now, I can tell you that the flux is equal to the magnetic field strength times the area enclosed by that wire times the cosine of theta. Right, so this is the general formula for flux. In the case where the flux cuts perpendicularly through the area, then you have that the flux is simply the magnetic field strength times the area, like this. And that's just because you can think of cos theta being equal to 1 because theta is equal to 0. Okay, again, let's just pause here. If anyone's got a question, please put your hand up. If not, can you give me an indication if you're happy with what's being said so far, please? Okay, cool. Nice. So let's just go back to these 3 points that we made here. We said, what are the 3 things that we can do if we want to get more rain passing through my hula hoop? Which is equivalent to asking, how do I increase the flux? The first thing we said was make it rain more heavily, which is equivalent to increasing the magnetic field strength. The second thing we said was use a bigger hula hoop because then more rain will fall through it. That's equivalent to increasing this area enclosed by our wire. And the third thing we said was we need to make sure that the tilt of the hoop is such that most of the rain will fall through. And that's equivalent to maximizing this term here. So if you want to maximize this, you maximize one or all of these things here. Right, so hopefully that just gives you a little bit of physical intuition about what this flux actually is. It's basically just how much of this stuff cuts through this area. That's just like a super basic way of thinking about what it is. A magnetic flux is how many magnetic field lines cut through a particular area. And we care about the proportion of them which cut through perpendicularly, which is why we introduce this theta here. Because another way of thinking about what that cosine theta does is it takes these field lines which are pointing in this direction and it calculates the component of them which actually cuts perpendicularly through the area like that. Right, you can do some trig to show that that's what that cosine theta is going to do. Okay, so that is essentially what magnetic flux is here. Musa.
Are there any units for flux?
Perfect question. Good. So let's have a look, because we know that the units on the left must be equal to the units on the right. Right, and now this, perfect question, Musa, this is going to tell us why the magnetic field strength is also called the magnetic flux density. So flux is B times A times cosine of theta. So the units of flux, we don't know what those are yet, sorry. So we know that the unit of magnetic field is the Tesla, and we know that the unit of area is meter squared. Does anyone know what cosine theta is measured in? What like physical units does that have? Musa?
Is it just degrees?
Right, so theta, it would be measured in degrees.
Oh.
Cosine theta is always just going to be a number. So it's just a number. It has no physical units. So therefore, the units of magnetic flux are Tesla meters squared. And this gets defined as, let me just quickly check. I'm pretty sure it's a Weber. Yes, good. It's a Weber. So 1 Weber is equal to 1 Tesla times 1 meter squared, like this. Now, this is just a new unit that's being introduced, by the way. So let's rearrange this formula to get the magnetic field strength. And it is the flux divided by the area times this cosine theta. But cosine theta is just a number, so we don't really need to worry about it for the argument that I'm about to make. So this is flux divided by area. So let me be careful here, because I'm going to use the word density, but the density that you're all used to is like mass divided by volume. Now, you can use the word density to mean other things. For example, I could talk about imagine that I showed you this pencil and I said it has a certain mass for a given length. Like if you chop 1 centimeter of it off, I can tell you what that mass is going to be. So I can define a mass per unit length of an object. And that is just another version of a density. So density doesn't always mean per unit volume. It can mean per unit area. It can mean per unit length. And in this particular case, the magnetic field strength is the magnetic flux density, where density is with respect to area, not with respect to volume. So this is why the magnetic field is also called the flux density. It just means what is the flux per unit area. So if we go back to that rain analogy, the flux was how much of the rain falls through my hula hoop. And then if I just normalize the size of my hula hoop to be, for example, 1 meter squared, then that would just tell me how much is it raining. And I would get the magnetic field like that. This isn't too important. It's just to give you an idea of why this is also called the magnetic flux density. Right? I don't think you'll ever get a question saying explain why B is also called the flux density, but it's just useful to know. Okay, so when it comes to questions like this, you might be asked to calculate the flux, but pretty much all of the questions about magnetic flux will actually be to do with what's called Faraday's law, which is what I'll come on to now. But let me just pause again. Can you all let me know, are we happy with anything? Does anyone have any questions? Okay. Right, so if you just look at this diagram, then this shows you how to define all of these different variables. So we've got flux, B, A, and theta. Okay, one final thing. Now imagine, Asif.
So, sorry, you know that equation BA cos theta?
Yes.
Will they ever give a question where theta is defined differently, but you have to like use trig to work out the right angle?
Yeah, that's a great question. It's possible, but I don't think it's very likely. Yeah, I don't think it's very likely, but this theta is the angle between B and the area, what I call the area vector, which is the vector which points perpendicularly out of the area.
Okay.
So if you can remember that is the definition of theta for this example, or for this part of the topic, then I think that should answer your question.
Okay, thank you.
Great, nice one. So let's go back to our hula hoop analogy, and we said now if I have one hula hoop with area A and it's raining an amount B, so the magnetic field strength is B, then actually let me also add in an angle just to make it more interesting. And I'm hula hooping at some angle theta, then we can work out the flux, which is B A cos theta. Right, so now imagine, let me try and make this a little bit. I mean, it's just a terrible diagram. Hopefully you all get the idea of what's happening. So this formula answers the question, how much rain falls through a single hula hoop? Now imagine that I've got, all right, maybe I'm like in a circus and I can do this with multiple hula hoops at the same time. And now I want to know how much rain falls through all of my hula hoops. And I'm going to say that I've got N of them. All I need to do is multiply both sides of this equation by N, because each one of them contributes the same flux. So if I've got N of them, I add N of them together, which is the same as just putting an N in front of the formula. Now, this equation probably looks quite strange because you would think, well, I've just got an n on both sides, so why don't I just cancel it? And that's a good question. And the answer is because this quantity here defines the flux, what's called the flux linkage. The flux linkage is n times the flux. Whereas just the letter phi is the flux by itself, which would be the case when n equals 1. So whenever you see or hear about flux linkage, we're talking about there being possibly more than one loop enclosing an area where a magnetic field is penetrating through that area. Okay, any questions here? No? Cool. So now I'm going to get on to Faraday's law, which is given by this equation here. But let's go back to our analogy again. And we'll try and make it make sense before. So let's imagine I'm doing my hula hoop and it starts off like this and it's raining a constant amount and my hula hoop is a fixed rigid size. So B and A are both fixed. They're not going to change. Right, and now imagine that I can do these tricks with my hula hoop where 1 minute it's going around in this direction and then I spin it around and it's going around in this direction. So that angle theta is constantly changing. So maybe the next second it's like this. And then I'm just sort of going back and forth between these two things here, right? If I could hula hoop, I would do a demonstration and then maybe this would make more sense. But hopefully everyone knows what I'm talking about here. So in this situation, theta is changing with respect to time. Because my hula hoop is going around my waist in like this fashion where it's changing angle constantly. And when this is the case, the flux is changing too. Because imagine at one instant in time, my hula hoop is going to be in that position where there will be the maximum amount of flux. And then maybe I can get it all the way up here where barely any rain is now falling through that hoop. So there's going to be a minimum amount of flux. So in this scenario, the flux changes with respect to time. Right, now imagine that I'm even better at doing this hula hoop and I've got multiple hoops around my waist at the same time. I can say that the flux linkage is changing with respect to time. And that's just a case where I might have more than one of these hoops around my waist. Now, if I can change the flux linkage with respect to time, which is what this quantity here means, it means a change in the flux linkage in a change in time, then an EMF, which is this quantity here, gets induced in the wire enclosing the area, so in my hula hoop. So a current would start to flow in my hula hoop if I was to do this, right? And then I would get electrocuted. And this is the basic idea of Faraday's law. It's if you can change the flux linkage with respect to time, you induce an EMF in the wire enclosing the area that you are penetrating the magnetic field through. And right, so that will cause a current to flow if there is an EMF. And the size of the current that you can produce depends on how quickly you can change the flux. It's not about how big you can make the flux, it's how quickly you can change it. So if you think about what this term is, if I was to plot a graph of the flux linkage with respect to time, can anyone tell me what this quantity here would represent of this graph? a change in n times, a change in the flux linkage over a change in time. What is that on a graph? Change in y over change in x? Musa?
The gradient.
Good. So the gradient of the flux time graph, or the flux linkage time graph, is what tells you how strong the EMF and the current that you're inducing is. It's got nothing to do with the absolute value. So how high up you are on this graph. Right, but let's ignore the graph for a moment, and let's just make sure that we understand this in words for now. So if I can change the flux linkage with respect to time, I can induce an EMF in the wire which encloses that area. And then downstream from this will be that a current will flow in this wire. So if we go back to this nicer diagram here, the idea is that we would coil a wire around like this. And this blue shaded region is just showing the area enclosed by this wire. Now, if I was to spin this wire around and change theta with respect to time, what would happen is that a current would flow in a particular direction around this wire for a certain amount of time. So if you think about what this means, I've just got a wire, right? Imagine I've just got a piece of metal that I've formed into a closed loop, and I put it inside a magnetic field. So maybe I just get two magnets like this, and I set up a magnetic field, and then I put a coil of wire into this magnetic field, and I spin it around like with my hands. If I do that, I can produce electricity because I can produce a current which flows in this coil. So in that sense, we can turn mechanical motion into electricity. Right, and this is how like generators work. You've got something spinning around and it produces a current. Okay, cool. Right, so I think we'll pause here. Let me just open up to the room. Has anyone got any questions that they want to ask before we do some questions? Akil?
It's a bit more of a basic one, but in the formula book, why is there a minus for this equation?
Yes. Okay, good. Right. So in this formula, in the formula sheet, and well, so you'll see here, this is a proportionality sign. It's not an equal sign. The proportionality constant in this equation is -1. The fact that that is true is called Lenz's law. And we will come on to that in the next lesson.
Thanks, sir.
But yeah, great question. So Faraday's law is the fact that the EMF is proportional to this change in flux over change in time. Lenz's law is the fact that there is a minus sign in the equation. So let me just write it down. It would be that the EMF is equal to the minus of the change of the flux linkage with respect to time. I think this is what you'll see in the formula sheet, right, Akil?
Yeah.
Yeah, perfect. Good. Nice. So this is Lenz's law. This is Faraday's law. Right, which is a little bit strange when you've got two laws for the same equation, but that's just because they both worked on it, and it's quite a hard problem to figure out like 200 years ago whenever they did it. Musa?
So did you say EMF was directly or indirectly proportional to time?
So I mean here, I don't know if you can say it's indirectly proportional to time, but it is directly proportional to the rate of change of flux linkage.
Okay.
Because if you was to say it's indirectly proportional to time, that would assume that this is a constant.
Yeah, okay.
And even then, this is a change in time, so I'm not too sure about that, Musa.
Right, that's fine, sir. Thanks.
All right, great, thanks. Isam?
Could you repeat the difference between Faraday and Lenz's law?
Yeah, sure. So Faraday's law is the fact that the EMF is just proportional to the change in flux linkage with respect to time. Lenz came along and said, no, it's not just proportional. It is the minus of the change in flux with respect to time.
Why would it be the minus?
That's a great question. And I will come on to that. I'll either ask Sajid to talk about that on Friday, or I'll cover that on Monday.
Right, thank you.
But yeah, that's a great question. But yeah, sorry, I can't answer it in a couple of minutes.